All right. So,
like the people that normally sit there, they just file in.
well, then I would have said like, oh, not you either, and not you, and not you, and not you. I got 1 minute.
Better.
I am. Yeah. I'm quite a bit better, which is why I'm so much more irritating.
Do you know what happened to you?
I had some kind of like lingering, like, I don't know, either inflamed sinuses or whatever. So I couldn't sleep and I couldn't stop coughing, and it was just a dry cough for days and days and days. So I've slowly recovered. But yeah, I've been sleeping, so I feel better now. So hopefully, since apparently like nobody else in here got deathly ill, except you. Yeah, I'm sorry. There were a couple people. Oh yeah, you were out. Never mind. A whole bunch of people were out. Try not to get sick before finals. That sucks. Oh yeah, if you're gonna get sick now and not 2 weeks from now. That's right. Well, I've already, whatever I have, I'm already over it. So when I'm blasting you guys with particulate matter now. Okay, so I posted a video that sort of covered some ideas from 6.1 and 6.2. So my plan for the week, So over the weekend, I posted sort of a study guide. And the study guide, if you haven't looked at it, includes formulas that I'm planning to give you. So there should be formulas there. There's no chapter 3. We have more than enough ideas that I don't need to go back and ask you guys about normal and tangential components of acceleration. So we're gonna restrict our attention to 4, 5, and 6.1. So the chapters that are covered are, I believe, 4.1, 4.2, 5.1 through 5.5, although that's not as daunting as it seems because iterated integrals are basically the same in any context. The hard things here are the change of variables and switching the order of integration. And then 6.1, but the big formula, the hard part about this is remembering which formulas are what, I think, anyway, right? There's just a lot of pieces to remember. Check the formula sheet. There's exercises I've pulled from the book that reflect all the ideas I have here. Yep. So I'm going to talk about delta F when we get there, right? So delta F is just the idea that we never actually defined what that was, except conceptually, which delta F tells you what the actual change in a function is. Delta F just means how much the surface move as you split around in a variable. The whole point of that was that DF is about equal to delta F. The total differential measures that. So now I did not put did I put the differential formula on there? The DF is equal to Fx1A. I did, H1. So yeah, that's yeah. So just practice the exercises so we get a chance. I want people to do that before we spend time as a class talking about it, because otherwise it's less useful if you haven't tried the exercises. You do not feel compelled to do every single one. I offered more than I thought people would necessarily want to do, so that if you had more questions that you wanted to answer, you could. Okay, so that you can see the kind of things I've been thinking about in the book. So I've got that study guide posted. I'm probably going to talk about that on, my goal is to talk about this on Wednesday. If people have questions about it, of course, you're welcome to come and talk about it to my office hours anytime you want. We've been working on these things. I'm going to talk about the study guide on Wednesday. What else did I want to say about this? My plan is to talk about 6.2 today. I do have a video posted if you need more details. 6.2 talks about Green's theorem, which is engineering departments think that 6.2 is the most important book in all of undergraduate mathematics. And the Green's theorem is sort of like one of the central ideas, and it is sort of the core idea of why vector calculus is useful, is what we're going to be talking about today. We're going to talk about, if I have a chance today, we can talk a little bit about 6.3, which is about conservative vector fields. And then next week, we're going to talk about the Stokes theorem, which is chapter 7.1 and 7.2. I guess there's an exam. Remember, there's an exam on Thursday. Okay, Yeah, so that's kind of my plan for the week, is to do that. If people don't have a ton of questions on Wednesday, then I will continue talking about chapter 6 and chapter 7. So these 2 weeks are sort of the culmination of the class in terms of the theory that we've been doing. It should make a lot of things clear. Now, there is something that goes beyond the course that I thought I was going to be able to do, but I slowed the class down to make sure that I was explaining the things that were going on in a way that I didn't originally plan. I borrowed somebody else's schedule and realized it was really, really, really ambitious to the point of just like blowing you away with stuff. So I slowed the class down, which means I'm not going to be able to probably talk about differential forms, which is sort of a contemporary way of studying differential geometry that shows up in high-level physics applications. If you're interested in differential forms and you're around in the summer or next year and you want to see kind of what's going on there, just come into my office and I'd be happy to walk you through it. It's a really cool kind of mathematics, but it's hard. I'm going to post a link to a paper by Terry Tao, sort of introducing kind of what's going on with differential forms. Okay, so any questions before I get started? Anything? Okay, so we need one last idea from 6.1. So there's a single idea that we're going to. How many of you guys actually watched the video I posted? Do not. If you didn't, it's cool. All right. So I like to think that I did a good job of explaining Green's theorem in that video. So I welcome you to watch it. There's an outside possibility that. So I'm going to be at a conference next week. I need to know, like, if what do you guys want me to do? You want me to teach synchronously, get a substitute in here, or do it with videos? There's probably 2 days I'm going to miss next week. Synchronously or asynchronously? Async? Well, I can do it synchronously and then record so that you get both versions. Or I could do it synchronously and asynchronously at the same time. So I'll do it in the time here and then also a recorded video. Would that be all right?
Yes.
So you prefer that to having like staff that's come in and do it? Like, it's really up to you. Like, I'm happy to have somebody come in here and run the class for me instead, if you guys want it in person.
I probably learned just as well through the videos.
All right, I'll do a combination. So the deal I'll make you is, if I'm going to miss class, I will be on the video synchronously, and I will record those, and I will also post my preparation notes as separate videos if you want to watch the digest version instead. Okay, so one of them will be more prepared, like this last one I posted, and the other one will be me teaching to a classroom of black boxes, the most depressing, or looking at you guys out on the lawns, and, you know, hanging out in the flowers and sunshine while I sit in my office or a hotel room. Anyway, I thought I should ask. Tuesday and Wednesday. So Monday is Monday's a holiday, right? So Monday is Memorial Day, and Tuesday and Wednesday.
As long as you teach.
What's that?
I just want you to.
Okay, I'll teach. That's fine. It's fine. I get it. I get it. This is just this conference. I normally wouldn't like go to a conference in the middle of like late in a quarter like this, but this is one I kind of have to go to, so I don't really have a lot of choice. I apologize.
What's the conference about?
Complex analysis, the greatest of all subjects.
That's why.
Okay. Right. So the thing that we defined with this guy, right? We defined this guy. What is that called? Now that was not on the video. This object is, what kind of thing is this? Don't say circulation. You don't know that's a closed path.
A vector line.
It's a vector line integral. That's right. And this was the sort of like formal notation for this, but we had a computational version of this as well that we wrote down, which was the integral from a to b of f of x of t dotted with x prime of t dt. Right? This is a thing that we did. The idea here is, what you should think about, this is the way of interpreting what this measures is, you can interpret this as the work done by F on an object traveling along X. You have some vector field, like an electric field, you've got a particle moving through it, this computes the work done. Okay. So there's another form that this gets written in all the time. It shows up in differential equations class, which is called the differential form of this. And it follows the observation that if you think about F, so F here, F is a vector valued function. So F has three components, right? There's an M. In fact, what they're going to say is imagine that F is equal to M F of X, Y, and Z is equal to M of X, Y, and Z I plus N of X, Y, and Z J plus P of X, Y, and Z. Okay. It's another way of thinking about what a vector field is. This is why we like short notation, by the way, is that this turns into a nightmare. But the idea is F takes in three coordinates and spits out a first coordinate, a second coordinate, and a third coordinate, right? Remember the I, J, and K here dictate vector coordinates. Another way of writing this would be like this.
Not put a minus in front of the
It's not a determinant this time.
Okay.
It's not a determinant. This is just saying that F takes in a vector and spits out a vector. Okay. Okay. So
I have a question.
Yep.
Are M and these are like functions?
They're functions. Yeah,
Okay.
M is a scalar function, right? So M is a scalar function, N is a scalar function, and P is a scalar function. But because it has a scalar function in the first slot, a scalar function in the second slot, a scalar function in the third slot, this is something that takes in a vector and spits out a vector.
Okay, so
These aren't, when I write this in shorthand notation, you're supposed to remember that this is a function of X, Y, and Z.
So kind of like M associated with F or something like that.
You should think here, like an example of this would be something like F of X and Y is equal to X squared YI plus YJ, which would be also the vector X squared Y. Here, M would be equal to X squared Y and N would be equal to Y,
Okay, thank you.
right? That's the idea of this. Okay, now X prime, you could think of as being X prime of T is like X prime of T, Y prime of T, Z prime of T. Right? X is a path. It has an X, a Y, and a Z variable, and it's parameterized in terms of time. So there's a move that gets made where you say, okay, well, if I take the dot product of this with this, F dot X prime of T as a vector dt is the same as M N P dotted with X prime, Y prime, Z prime dt, which gets us this form. M X prime of T dt plus N Y prime of T dt plus P C prime of T dt. It's all just notation, right? It's a way of making better notation for these things. And then there's one more move to make, which is to notice that X prime of T dt, we call that dx. That's the differential in X. So X prime of T dt, this dude right here is what we call dx. That's the same dx we'd use in calculus, by the way, when we do a substitution. And this is dy, and this, not P here, but the Z of T dt, this is called dz. And so the final sort of form of this is to say, so this is kind of an engineer applied mathematician differential equations form, is to write F dot X prime of T dt as M dx plus N dy plus P dt. And if you remember your differential equations, this got thrown around all the time in differential equations without ever telling you why it was the form, where it came from. They started writing differential equations down involving this thing. But it really is just the idea that you're taking a dot product of a path, the derivative of a path with a vector field. Yep.
Can you explain why it's work again?
Why it's work?
Yeah, like why does this formula?
Oh,
calculate
because
it?
what you're doing here is this is computing the direction and velocity of the path that you're traveling on. And then you're dotting it with the force field. And what that says is how much of the force is pointing into the direction that you're traveling. That's what a dot product of vectors does, right? So it's work because if you're on some path and this is your velocity and this is your force, then the dot product of those two vectors measures how much, you're basically picking up information about this projection. You're projecting the force vector onto the direction that you're traveling. And that's how, and then you add all those up and you get work.
Okay, thank you.
Okay, so this is called the differential form of an equation. It's and so when you see it, if you ever see something that's written down in that way, just remember that if I write, say, in two variables, x f dot ds is equal to the integral over x of m dx plus n dy, these are the same thing. In both cases, you are required to have chosen a path, and then you do the substitution dx is equal to x prime of t dt. So this is normally used as a symbolic way of writing a path down, but when you compute with it, you actually have to know the path so that you can substitute in. Don't worry, I'll do an example of this when I actually write Green's theorem down here. Okay, so without fanfare and without really explaining what's going on, the book just writes down Green's theorem. And there's a bunch of conditions that need to hold, but this is Green's theorem. So maybe the single most important theorem in vector calculus. And what Green's theorem says is the following. If you have some domain D, well, a domain D has a boundary. So the boundary is a set of curves that are on the outside of the domain. So this curve right here, this curve C that travels around D, C is equal to the boundary of D. It's a simple curve, which means it doesn't cross itself. It's closed, which means it has a starting point and an end point that are the same, so it's a loop. And we set it up so that as we travel around the curve, the domain is always to the left-hand side. So we have to choose an orientation when we do this. And we're always going to choose so that the boundary has the domain on the left. So in this context, any parameterization I chose of this, any path X that I choose that has C as the output curve has to travel so that it's got the domain on the left-hand side. Okay. So D is called the domain. C, which is the symbol partial D, means the boundary, is called the boundary of D. And what Green's theorem does is it connects the behavior of a function on the inside of a domain to the behavior of the function on the boundary.
Is that the derivative?
No, and you got to be careful here. That symbol means boundary. When you apply that partial symbol to a set, it means the boundary of the set. I know it's a weird symbol to use. It's just standard. I have to use it because Holly does and everyone else does too. So yeah, it's not a derivative. It's the edge of the set. Okay, so what Green's theorem says is that if f of x and y is C1, so f of x and y is equal to m of x and y, n of x and y. So this is a theorem that holds in two variables. This is a two-variable theorem. Green's theorem holds in R2. If f of x and y is a vector field on R2, and f is C1, derivatives are continuous, and the domain is set up correctly. I mean, there's conditions in the domain that we can go into, but the basic idea is the boundary is well behaved. Okay, the boundary doesn't cross itself, and everything loops up really nice. Then where you get to start using fancy symbols in your math. M dx plus n dy is equal to double integral d over the partial of n with respect to x minus the partial of m with respect to y dx dy. Okay. This on its face looks like, what the hell am I even saying? I just wrote a bunch of symbols down at you. In fact, symbols that, looks like we're starting to write in crazy crazy mathematics language here. So let me see if I can like clarify what, so that loop symbol there means only that you're integrating around a closed loop. That's all it means, all the way around the boundary. So the circle around an integral only means that C is a closed loop, And actually, does that condition, does this look familiar to anybody? dn dx minus dm dy. Man, that sure seems familiar. It looks like an exact differential equation. Differential equations. In fact, you probably spent a whole lot of time dealing with checking that this thing was equal to 0, and then maybe finding an integrating factor and multiplying it in without having any idea what you were doing. So yeah, so this actually is where exact equations come from, right? It comes from this integral right here. So I'm going to try to like give you an idea of what is going on with this integral, what we're actually measuring. The first thing is that this, in some sense, is picking up the rotation of a vector field, right? Exactness in a differential equation. Actually, let's even go further than that. What did exactness let you do in a differential equation? Do you remember what an exact equation let you do? See, you guys, you remember that part, but nobody remembers what it does. Okay, we'll leave that for the magical world of conservative vector fields. We'll get back to it. Let's actually talk about what this is measuring, what it's doing. So you guys remember the fundamental theorem of calculus says that if f prime is equal to f, then the integral from a to b of little f is equal to big F of b minus big F of a, right? So what that's telling you is, oh, look, there's a, there's b. You can think about this integral on the boundary as like this part. Because what is this telling you? F of b minus f of a is telling you evaluate the antiderivative literally at 2 points. Evaluate the antiderivative at the boundary, right? This doesn't see anything going on in the middle. It just sees what happens at a and b, and then you subtract. And it's an integral. Okay. Well, if you took the derivative of this, I mean, this in some sense is like a derivative of this thing. This is kind of like an integral of this. Okay. And so what are we relating this to? Well, this thing, whatever this is measuring about the vector field, this quantity, this differential quantity in the middle here, whatever it's measuring, we're adding it up over the inside of B. Well, that's like what this is, right? This is telling us something about the inside. This quantity tells us what happens in the middle. In the middle, there's this function little f that's wiggling around. And we're adding up the interior, what's going on in the interior of the interval. And we're saying, I can do this either way. The area under f in the inside of the interval from a to b is the same as this big fat function evaluated at b and a and then subtract. There's no reason to believe these should be connected. So the same idea works here. Why this is so useful. Notice I've given you no physical interpretation yet, but I promise I'm going to. The idea is the power of this technique is it gives you a way of connecting functions defined on the inside of a domain, which are double integrals, to functions that are just line integrals defined on the outside. So from a physics, engineering, applied mathematics, and pure mathematics standpoint, this says I can tell what's going on the inside of a domain only by looking at the edge, which is weird and powerful. I don't care what's going on. You know, if I had one of these, I could compute it just by tracking what's happening on the edge. Okay. So you can think of this as representing a function. It has some surface that it defines that you're computing the volume of. So you find the volume under this thing, or you could just pile up this area on the edge and you get the same number. So this should strike you as a really weird theorem that you can move back and forth between functions defined on a two-dimensional domain and functions defined on a one-dimensional curve. Really different. So let me see if I can give you an interpretation of why. Well, actually, maybe first I should give you an example that this actually does something. Like, let's do an example of what this looks like. Let's look at this. Let's look at f is equal to, it'll be a good chance to practice. You guys can ask me questions if you have them. X, y, I plus y squared j. And let's let D be the region between y equals x squared and y equals x in quadrant 1. Okay, so here's your region. So this is D, right? Now, based on the work that we've done in 6.1, if I wrote down that I would like you to compute the double integral over D of f dot ds, not even dot ds, sorry. I'm lying to you. It's dA, right? It's the double integral over D of delta n delta x minus delta m over delta y dx dy. You should be able to do that. That's an integral that's easy to compute. What am I going to do with the region D? How am I going to turn that into an iterated integral? If this is y equals x squared, and this is y equals x, how do I turn this into an iterated integral to solve it? I somehow have to take this region and convert it into like a double integral, right? We did that all through 5.1 and 5.2. Well, for a fixed value of x, which y values do you travel through? You start at x squared, and then you go up until you get to x. So your y values travel from x squared to x. For a given x, you travel from x squared to x. What do the x values travel through? From 0 to 1. So x values travel from 0 to 1. So at least I can do that part. The integral from 0 to 1 of the integral from x to x squared to x. And now I've got to do the integrand. What are m and n in this problem? The n is y squared, the m is xy. This is m. This is n. So dn dx is 0. And dm dy is x. Wow. Well, that's pretty easy. Do you think it would be okay if I just like wrote the answer down? Would you really want me to integrate that? I know I have scintillating integration skills. You guys love watching me do algebra on the board, but yeah, if you do that, you get -1/12 out. Just polynomial integration. Integrate in y first. I have to resist the temptation. It's hard to, you do me a math teacher long enough and you see a polynomial with an integral sign on front of it. What's up? Oh, okay. Remember, dx dy here, really secretly, this should be dA, right? I chose the order of integration the way I did because of the way I characterized the region. Since I chose y first and then I integrated through x, that's why I set it up dy dx. Yeah, it's really up to you to choose the correct dA. That doesn't change. This is always the same. No matter what you do with dA, this is always the same. Okay, that's easy. That's a nice way to do that integral. Man, it sure would be tough if somebody came along and said, I'd really like to know what the integral over the boundary of D of f dot ds is. And of course, the first thing you say is, oh, Green's theorem applies, so it's equal to -1/12. Yep.
One question. We made the m dy as equal to x. Why didn't we choose -x in the integral?
Oh, we should have chosen -x. That's actually where the minus came from. You're right. Yeah, because it's dn dx minus dm dy. There should have been a negative there. Yeah. Thanks for catching that. Yep, it's 0 minus x. Okay, now the annoying thing about Green's theorem is that before you get access to its full power, you have to go through garbage like this, where I say, now I'd like you to compute this line integral around the boundary of this region and prove to me that they're the same, which means you have to parameterize the boundary. You got to come up with a path x that actually does this for you. So your first job, if you want to track around the boundary, is to say, well, what is the boundary? I'm going to start at 0, 0. I'm going to track along the curve y equals x squared until I get to here. So let's parameterize that first. How could I parameterize that? Well, and I have to travel this way because the region is going to be on this side, right? So one way to parameterize that first part is to use x of t is equal to t squared. Starts at 0, 0, ends at 1, 1, and is always sitting on the curve t squared, right? That gets me the first part of the way on the path, on just the parabolic part. Now I'm at 1, 1. Oh, and I should say the t values here range from 0 to 1. Now I'm at 1, 1, and I need to go back to 0, 0. How do I do that? Well, I start at 1, 1, and I want to end at 0, 0, because orientation matters. So for my second part of the path, I'm going to choose 1 minus t, 1 minus t. That's a straight line that connects 1, 1 to 0, 0. I start at the point 1, 1, and as t ends up at 1, I end up at the point 0, 0. So again, here, t goes from 0 to 1. This is a typical move in a problem like this, to have to parameterize the path. Now, the obnoxious thing is, that means that this is actually this is an integral in two pieces. One piece that corresponds to this parameterization, and another piece that corresponds to that one. So we have to think about this as being the integral of C1 f dot ds plus the integral over C2 of f dot ds. And since each of the parameterizations is different, even the numbers I plug in are going to be different. So what is the integral over C1? Well, it's the integral from 0 to 1 of f of t and t squared dotted with ds. And what's ds? What's the vector version of ds? X prime of t dt. So x prime of t is 1, 2t dt. This is the integral that represents just the contribution on the first part of the path. Then I have to add that to the contribution on the second path where the parameterization changes. That's the irritating part. So the second path is the integral from 0 to 1 of f of 1 minus t, 1 minus t, dotted with a different dx dt, which is what, minus 1 dt. And this is why we actually have to break this up, because the numbers that I plug into f are different. I can't use x and y. I've got to use the path that I'm stuck to. So if you were setting this integral up, the last step would be to do this. So what was f equal? Oh my God, I deleted f. F is f xy squared comma y? xy, oh, it's xy and y squared. Okay, so on the first integral, we get the integral from 0 to 1. So I need f, but with t and t squared plugged in. So I get t times t squared. That's xy comma t to the 4th, dotted with 1, 2t dt. That's this first integral. Plus the integral from 0 to 1. Okay, now the same f, but with those plugged in. Oh man, not a chance in hell I'm doing this on the board. Okay, so there's the first component of f. And the second component of f is this. And I have to dot that with, at least it's only dotted with minus 1, 1. And this is why you appreciate Green's theorem, because who the hell wants to do that? Would it shock you to learn that if you took these dot products and integrated everything with respect to t, then minus 112 will come out the side? Probably not, because I asserted that it was true by Green's theorem. So you can check this by hand if you want, but like the idea is if I ask you to set up an integral on the boundary, this is what you need to do to set up the integral on the boundary, right? This is a parameterized integral where this piece is the sort of C1 piece. This part works for C1 and this part works for C2. And it's typical to have the boundary broken into pieces where the parameterizations are different on each piece. So
Where did you get the 1 from 2t for C1?
that is the derivative x prime. The derivative of t is 1. The derivative of t squared is 2t. So if you're going back to look at this, this piece right here, this is f of x of t, and this is x prime of t dt. But then I had to change the x when I went to the second integral because we have different functions, right? So again, this piece is f of x2, say x1, and this piece is x2 prime t. So two paths, two parameterizations, two integrals. Okay. So at least that's an argument for like, it's nicer usually to do things on the boundary, or sorry, sometimes it's easier to work in the middle than on the boundary. Sometimes you work on the boundary than the middle. Can I erase this? Okay, I mean, I know that a lot of people prefer that I don't put examples up or that I do too many examples. I apologize. This is sort of like, it's a hard class because I have to like walk the line between theory and application here. So there's another observation that you might make, which is if you look at this integral, last time what we talked about was the idea of circulation of a vector field, right? So if X was a closed path, if I have some closed path C, we actually said, oh, well, one thing that you could think about this representing is circulation, which was something like net volume flow, net volume of water through or around net, maybe not net like volume, but like net flow of water around the curve C. The idea was we thought, oh, well, if I've got some little contribution on the edge here and this path is moving this way, and I can think of this as being x prime of t telling me what direction, as I go around the path and I have some f telling me how the water is moving, and I integrate all the way around, somehow what I'm doing is I'm adding up all the flow all the way around. And what I'm keeping track of is what's the sort of total circulation around that curve if the water is swirling, right? So you might get the idea that Green's theorem might have something to say about the relationship between the circulation which we defined on this circle and the behavior of the vector field in the interior, right? And in fact, there was a quantity that we talked about where we talked about rotation of vector fields. I mean, circulation is sort of a measure of how the vector field is turning this entire region, right? You can think about there's some body of water that's being twisted around the edge, and that's what circulation is keeping track of. What's the total sort of twist of the water around this curve? What was the quantity associated with vector fields that measured how a vector field is twisting? It's curl. Can you remind me what the definition of curl is? So the curl of F had something to do with twisting. It's like this had something to do with rotation. How do we define it? Well, del cross F. Gotta be careful. Yeah. Okay, what is del cross F? Okay, so of course a cross product only makes sense in 3 variables, right? But in this, okay, you ready for the greatest swindle that vector analysis ever pulled? So it turns out everything in 2 dimensions is really secretly in 3 dimensions with 0 in the 3rd dimension. So you can use all 3-dimensional vector analysis on 2 variable functions by just pretending that they're sitting in a flat space. So you might think, I can't possibly take the curl of a 2-dimensional vector field, but you can, because you just put a 0 in the last slot. Remember, this was defined for an F that took R2 to R2. So instead, what we're going to do is we're going to cheat. So imagine instead that you had, if you were given an F that was an M dx and M n. So F is a vector field from R2 to R2. You really wanted to compute its curl. Well, you could think about F as being a vector field from R3 to R3 by instead looking at mn0. Put a 0 in the z slot, right? F's not doing anything in the z direction, so put a 0 there. Now, this f takes R3 to R3, and that means I'm allowed to take its curl. Curl is valid on a three-dimensional vector field. So let's do it. Let's, for mn0, let's take the curl of f. Rad cross f is equal to, everybody remembers this, I'm sure. Vector 3. I, j, k, d by dx, d by dy, d by dz, m, n, 0. So you compute that determinant. Let's see what happens. The y derivative of 0 is, when I subtract off the z derivative of n. Wait, did I do something wrong? Hold on a second. Yeah, okay. It didn't. What's this derivative? What's that derivative? Why is it 0? Because n doesn't have any z's in it, right? M is just a function of x. Oh man, what a scam this is, right? Oh, so that means that this thing is equal to 0 in the I direction. All right, let's check the j direction. Maybe something more interesting is happening. Minus something j. Okay, what happens in the j direction? So we got the x derivative of 0, which is, and the z derivative, oh man, the z derivative of m is also 0 because n doesn't have any z's in it. N is a function of x and y. Oh, that's also 0. Well, what happens in the k direction? This isn't saying very much that's interesting. Okay, let's see. D by dx of n, the n dx, minus, oh, look at that. That looks familiar. This quantity right here is the same quantity from Green's theorem. Huh. So that means what Green's theorem is really telling us, thinking about it this way, right, is that the total circulation of fluid around a curve is somehow equal to the sum of all of the infinitesimal rotations on the inside. So if I add up all of the rotations in the interior, the sum of all those infinitesimal rotations will tell us the total rotation around the edge. That's kind of what this does. The curl of f is the quantity that shows up in Green's theorem. And so you get what's called, this is called the, this is a name. This is called the 2D Stokes theorem. What it says is the following. The integral around f, I'm going to get the exact same language as the book. The boundary of f dot ds is equal to my dying laptop battery. I'm ready to get it plugged in before it fails. I know. About the punchline. I save it. Yeah, okay. Okay, we're safe. Okay, so now let's finish the punchline. Is equal to the double integral over d of the curl of f dotted with k dA. Now, what is this k doing in here? The k is just here because this gives us the axis of rotation of the vector field, right? All this rotation is happening in the xy plane, and so the z must be pointed straight up. So the fact that there's a dot product here is an artifact of the fact that we've cheated in this vector notation by thinking of this as a three-dimensional vector field instead of a two-dimensional vector field. And I have to take the dot product to get it back down into a scalar again. Yep. Yes, k is the z, it's the unit vector in the z direction. And so this is a striking application of this. Again, this is called the 2D Stokes theorem. And what this tells you is that the circulation around the edge of a vector field is equal to the total infinitesimal rotation in the interior. This is a major result in physics, that you have this relationship. Okay? The infinitesimal, total infinitesimal curl or rotation in the interior is equal to circulation around the boundary. That gets used all the time. again, from a physical standpoint or applied mathematics standpoint, the fact that you can tell something about what's going on in the interior just by looking at behavior on the edge, oftentimes in a physical application, you only have access to what's happening at the boundary. You might not be able to see inside. But if you can see the outside, you've got some picture of what's happening in the interior. And that's what kind of Green's theorem lets you get back and forth between. Okay, now there's one other quantity we might think to do. Oh, wait, if we could cheese curl into this picture and Green's theorem suddenly turns into this thing that measures curl of vector fields. What if we decided, well, I don't want to talk about rotation, I want to talk about flux instead. I'm going to draw a different picture. How about instead of tracking the effect of the vector field parallel to the curve, I track the action of the vector field perpendicular to the curve that I'm traveling around. So what I mean there is, if I start with some region, so this is like version 3. This was version 2 of Green's theorem. Version 3 says, well, what if instead I've got some C and I'm traveling around it? And this time what I want to do is I want to figure out not what F is doing with relation to these tangent vectors, but what F is doing with relation to normal vectors instead. If I do tangent vectors, I get the idea of fluid swirling around this thing. If I do normal vectors, and I have some vector field, and I take these dot products, so here's a vector field here, there's F, and say F is right here, and F is right here, and maybe over here in this direction, there's another normal vector N. I have an F pointing in here. What am I measuring now? So like, just imagine for a second, just with this setup right here, without telling you anything else. What does this measure? If I took F, not dot T, not dot the X prime, but instead I did F dot N, what am I measuring with this? This measured flow, like, you know, how much the force field is pushing fluid along the curve. What is this measuring? Can you say it without referring to, you say it without saying the word flux, because a lot of people here may not know what flux is. So this is going to connect to divergence. So go back to over here. Yeah, thinking about it as fluid, it's basically keeping track of how much fluid is flowing through the boundary in total, right? What you're doing when you add up all these things on the boundary here is you're keeping track of what's the total net flow of fluid through this curve. Now, net flow of fluid, so again, you can imagine that if you took this and you integrated it around the boundary, that you would end up with something like NDS, but this is going to be something like total flow through the boundary of D. And in physics, this is the quantity known as flux, how much of a field is passing through a surface. Okay. But that's going to connect, if curl connected rotation at the boundary to little itty bitty rotations in the interior, maybe fluid flow through the boundary can be gotten by adding up little itty bitty fluid flows in the interior. Like if I picked a little point in here and I put a little square or circle around it, and I kept track of how much fluid flow was going in and out of that, and I added it up over the whole region, maybe the total of all those is also going to equal to the flux through the boundary. There's a name for a little tiny box that I'm keeping track of how much fluid, net fluid is flowing in and flowing out. And it's called divergence. So the divergence form of Green's theorem says, well, the circulation form connects flow around the boundary to curl on the inside. The divergence form is going to say flux through the boundary is equal to divergence, the total divergence in the interior. And that looks like this. This is called the divergence theorem. So these three theorems are sort of the spinal cord, if you will, or the spine of multivariable calculus in physics. So if you go on in any sort of higher level applications in physics or engineering, one of the things you'll see is that all the field equations are built out of moving back and forth out of these types of ideas. And like motion through a boundary is equivalent to adding up some sort of behavior in the interior. So these three theorems are the bedrock theorems of vector analysis and application. So Green's theorem, the rotational version of Green's theorem involving the curl, which is called 2D Stokes theorem, and the two-dimensional divergence theorem, which tells you that flux through the boundary is equal to total divergence in the interior. So again, flux through the boundary, amount of fluid flow throwing through the boundary is equal to the total infinitesimal flows in the interior. Rotation in the boundary is equal to total infinitesimal rotations in the interior. And then finally, the classical Green theorem, which actually measures something different we'll talk about next time, says this. F dot ds is equal to the double integral over d of what the hell was it? dn dx minus dm dy dA. And I'll tell you, just to point out to what's coming, this theorem, I'll turn it this way so people can see. This theorem actually measures the failure of a vector field to be conservative. The failure of a vector field, if this quantity is not zero, if this is not an exact equation, it means that traveling from one point to another along different paths gives you different answers. Which is the same thing as saying you carry a bag of sand to the top of the Empire State Building and come back down again. Physics says you did no work, right? Physics says you didn't do any work, right? The bag ended where it started. If you do it in a place where this is not zero, you do work. And that's not the sort of physics that, the fields that come up in physics don't work like that. So Green's theorem is most useful because one, it describes this rotational and divergence theorem. And two, because it's connected up with the idea of conservative vector fields that we'll talk about next time. Okay. All right. So I have not posted homework on 6.2 yet, or 6.3, but I will post that probably either this afternoon or tomorrow. For now, what I want you guys to focus on is getting ready for this test.
I confirm really quick that my cross product is.
Okay.